In part two, we looked at different features of chemical product and how they can influence the objectives and priorities that we set for our chemical process design. Now, let's see how a chemical engineering design problem is formulated. Before we start the process design, we have to formulate the design problem. And this begins with product specifications. If a well-defined and well-established product is to be manufactured, then the product specifications is straightforward. However, for specialty products to be manufactured, the functional properties are more important than chemical properties. Okay, and hence we have to go for the product design step prior to the process design. So what it means that in order to start our process design, the first thing that we need to do is define the need for our process design. Okay, and this slide focuses on what design is in the broadest term beyond and including chemical engineering. Design generally aims to solve problems or meet a perceived need. I guess this definition might fail if you are thinking about design of the latest iPhone, but let's go with this definition for the moment. So the first step is to define the needs specifically enough to allow the technical solution to be assessed in terms of whether it solves that problem or not. Okay. So we need to also understand the constraints as well, and these constraints could be related to the cost, size, weight, or health and safety, or robustness of the plant. And this could also be these constraints could also be the legal constraints that we have from the governments, for example, in terms of the pollution or the safety of the plant as well. And as I said, that the definition of the problem itself is not always straightforward, especially if you are talking about specialty chemicals, where actually you have to think about the product design before you start the process design. Okay. The second step is to develop the solution that meet the needs. Okay. So where do these solutions come from? Well, this is actually interesting because often time these new solutions are derived from existing solutions. Okay, so more like, for example, the new version of iPhone that just is kind of an updated version of an older iPhone. Okay, nevertheless, this is where creativity is needed, complemented by technical competence. The third step is to assess solutions being developed. Okay, do they meet the defined needs, and are they technically feasible, or do they satisfy the constraints, and at what cost? And once we have our design, we need to evaluate it against performance criteria. Okay, and these two arrows remind us here actually that design is an iterative process, and the first solution that we develop might not be the best solution or might not be selected, and we might need to go back and develop our solution further before it is finally selected. Okay, but this iteration takes quite some time, and engineering time obviously costs money. So therefore, the methods for evaluating design alternatives need to be time efficient. And one way of saving time is to use simplified approaches, giving approximate answers first. And these simplified approaches can help to shortlist, for example, most of the promising solutions, and then we can carry out the detailed evaluations for a relatively smaller set of potential solutions. And this is how we can actually save our engineering time. The design of chemical and biochemical processes involves process synthesis, process design, process simulation, and process integration. And these activities are complementary and very often iterative in nature. Okay, so this slide defines various activities and show the connection between them. So for process synthesis, that is also the focus of this unit. involves selection of the series of process steps and the connection between them. And the units and the how we connect them is what we call configuration of a flow sheet, and we will look at in the next slides and in the next lectures as well. In the case of process design, we talk about those units and configurations and identify suitable operating conditions and work out how big the equipment needs to be and what it will cost. Okay, so we will look at the size of the equipment and also its economics as well. Then we have the next step of process simulation, where actually we take the design and its configuration and look into mathematical models where we can actually predict performance of that particular configuration or plant. Okay, and these models are typically built on understanding of our first principles, for example, chemistry, thermodynamics, mass transfer, heat transfer, and material balance. And in some cases, we also use empirical relationship because it is not easy to define everything based on first principles. But if we use empirical relations or equations for the design of our system, then we need to actually pay more attention in terms of the validity of those equations in terms of the process conditions. Finally, we have the step of process integration. And process integration mainly includes heat integration, especially in the design of heat exchanger network or in terms of effective utility design. Process integration also considers interactions between different process steps and how to exploit these. And one example of interaction are those between heat generation, heat power generation in terms of steam systems. Other examples are interaction between reaction and separation processes in a flow sheet via the recycle or interaction in terms of sequence between two or more distillation columns. So the aim of process design is to find the best process design considering the process technical feasibility, its safety in terms of operation, and profit in terms of economic considerations. So the same information that I discussed in previous slide is shown here graphically, where we have process synthesis that considers individual unit operations or equipments. And for example, we have reaction, separation, mixing, heating, cooling, pressure change, and then how we can best connect these equipments. And then we can have different, obviously, alternative ways of connecting different equipments to get the final product. Once we have our finalized or configured flow sheet, we start looking into design. And in design of our process, we look at what size and cost of equipment that we need, and we can change the operating conditions towards identifying the best possible performance. And finally, we have process integration that considers the whole flow sheet and the interaction between different units, especially but not exclusively the energy related interactions. But we can also look at different interactions like how the recycle ratio and the reactor conversion can affect, for example, the distillation column operation, and also if we have more than 2 or 3 distillation column, how we can sequence them to recover the energy from it. So the design of a process typically happens in stages with repeated evaluation as the design is developed. So we start with the first step of design appraisal, which explores various high-level questions. For example, is there need or demand for the product or products? Are technologies available to convert the raw material into those products? And are those technologies mature enough, or how mature are they? And finally, it looks at the economics of the project. So is it possible that the process being designed could be more economical? Remember that at this stage, we have little information beyond what are the raw materials and what the products are going to be. Okay. However, a negative answer to this question is helpful for making a go no go decision to avoid spending any more time and resources in design activities. The next step is the process design concept, this step looks at the proposed process in a little bit more detail and put together a flow sheet. And the flow sheet normally includes, for example, different processing steps and what unit operations to include, and also what are the associated operating conditions, or at least a rough estimate of these operating conditions. At this stage, you should have enough information to look at the safety of the plant and what are the implications of different steps. But also it allows us to look at economic viability of these proposed processes. Okay, again, it is too early to give more correct values, but it is more like approximate values just to decide that if it is a go or no go decision for making this plant. Once you have the preliminary concept developed, or you have the preliminary flow sheet of the process, then you look into feasibility assessment step. And in feasibility assessment step, you have much more detail of the process. The scope increases to consider, for example, operational issues such as how we start up, how we shut down the process, and how to ensure a safe operation. Okay. So the details of equipment, also known as plant, significantly increase compared to preliminary design development. The next step is detailed design phase, and that focus on equipment as well as on associated sensors, controls, and other connections. Okay, and at some point, the equipment must be ordered from an equipment vendor or manufacturer, and there must be detailed plans about how the equipment will be operated. So then you need information about, for example, how the equipment will be, or the plant will be operated in normal conditions, how it will be operated in starts up or shutdowns, what will be the emergency shutdown procedures, and other special operating conditions all need to be taken into account. And by the time you are ordering equipment, costs are fixed because you have already put tenders out for the equipment. So then you can do a much better economic calculation of the process. And finally, you have the fabrication step where actual equipment that you ordered is installed and commissioned. Figure 1.4 in chapter 1 of Sinot and Towler textbook gives much more detail, especially about detailed design phase. So please have a look at it in order to get more information about different aspects of design. The type of the process affects process synthesis. For example, we talked about different types of chemical products, and if we look at, in particular, for example, for bulk product or bulk chemicals, the margin, the difference between the value of the product and the cost of the raw materials, tends to be low. Okay, so this puts a lot of focus on efficiency or the process innovation to reduce the processing cost, because the margins are quite low. So we want to make our process as efficient as possible so that we don't have to spend high operating costs, so that we can generate more profit from our overall process. On the other hand, for specialty chemicals, because we have high added value products, so we can afford to spend on high energy, for example, intensive processes, because we will still generate significant profit out of the process. Okay, but for the case of specialty chemicals, we have other issues, like, for example, if a specialty chemical is protected by the patent for, let's say, a limited time, then the emphasis for that, for the specialty chemical, is to getting the product to the market swiftly. It means that we have to work for the product design and the process design simultaneously, because we don't have time to develop the product design first and then convert that product design into process design. Okay, so most oftenly they work together so that we can actually make the best use of this patent protection and generate profit from the process. Here we don't have time to discuss the full range or types of products and processes and how they affect our choices in terms of process synthesis and process design. Here we simply note that the synthesis of batch processes and biochemical introduces new challenges and constraints in the process design or process synthesis. For example, if you have a batch process, you have to think about in terms of changing process conditions and how to accommodate that, different equipment cleaning and storing. And let's say if you have a distillation column in your batch process, so how to run that distillation column in a batch process, okay, because you might need to separate some chemicals. Very often, we don't have pure batch or pure continuous processes, but normally a hybrid of the two. So, for example, if you have a hybrid batch process with a distillation column, you can actually store the chemical from different batches in a tank and then run the distillation column in a continuous phase. So that is more like hybrid batch process. For the case of biochemical processes, because we use enzymes and bacteria and microorganisms, so we have additional constraints to maintain our process conditions so that we don't actually kill our enzymes or our bacteria. Okay. And finally, we have the product design that is very important in terms of specialty chemicals. Okay. So, for example, if you are designing a specialty chemical and halfway through its life you decided to change its formulation, so before you look into the process design and what challenges you have for the process design, you have to first look into different properties of the product that you want to design. And once you finalize the properties of the product, then you will start looking at how to generate or how to synthesize that specific product in terms of the process synthesis. So all these factors or points that we discuss in this slide, they are going to add additional challenges to our process design. The hierarchy of chemical process design can be represented symbolically by the layers of onion diagram. And I hope you have seen this more than once already in your studies. And it emphasizes that the design choices made at one level impact on those in the next level. The fundamental transformation of raw materials to intermediate and final products almost always takes place in the reactor, and the reactor dictates the conditions of the feed and the products, and therefore the pre and post reaction separation requirements are also set based on the reactor conditions. And once you know your separation requirements based on what kind of effluent reactor you are going to process, you start looking into heat recovery systems. Okay, and these heat recovery systems depend on the reaction, separation, and cycle flow sheet that you have designed. Okay. Then you have the need for utilities, and they depend on, for example, what kind of heat you recovered from within the system and what you couldn't recover. And then if you still have some additional heat or cooling requirement, then you use external heating and cooling utilities. And finally, you look at water and effluent treatment, and that is also linked with heating and cooling requirement as well. And also depend on, for example, if you have effluent gas or liquid or solid phase, and then you can decide your treatment for the effluent. The onion diagram then sets the sequence for the process synthesis and for the collection of the necessary information. Please read through the notes on the slide. The note at the end of the slide reminds us that the material used and produced along with the processing steps introduce process hazards. We can increase the safety of our process by considering these hazards and how to avoid them as we work through each layer of the onion.